In this video, we'll look at what applications you can tackle with Hadoop. Next, the market and technology drivers that led to the explosion in Hadoop adoption. We'll describe the essential components of Hadoop, as well as the ecosystem of tools that have grown up around it. Finally, we'll take a high-level look at MapReduce because it is the fundamental paradigm shift that makes Hadoop so powerful. Let's start by looking at who uses Hadoop and what they do with it. It turns out you probably are already benefiting from Hadoop in your day-to-day life. Hadoop's initial development and popularity was driven by well-known internet companies like Facebook, Twitter, and others. These companies have millions of users daily, producing huge streams of data with lots of information about user preferences. They found out they could use this data to target content to viewers, making their products more useful and their ads more relevant. Much of the early Hadoop code and tools arose directly from real-world applications of these companies. But not everybody is a social media company. Today, it's likely that your daily credit card transactions are also processed with Hadoop for fraud protection. Hadoop has been revolutionary in enabling new kinds of analyses that were never possible before. Some hallmarks of Hadoop are iterating on a whole dataset and longer spans of data, not just a sample set. Including multiple data sources beyond just structured records in an enterprise database, accepting schemaless data for which you might not even know the format until you start analyzing it. For businesses whose operations rely on the ability to make decisions based on emergent trends in a growing number of sources, Hadoop has become the indispensable tool for big data processing. Among the thousands of MapR installations, here's a small sampling of applications for Hadoop. First, just notice the brands here. The list includes big and small companies across all sectors. McAfee, the internet security and virus protection company, uses Hadoop to perform domain and email reputation scoring to recognize signatures of hackers. One of the major credit card companies uses Hadoop to turn customer transaction history into intelligent recommendations for affiliate products. TSMC, the world's largest semiconductor foundry, uses Hadoop to predict failures based on signatures from instrument measurements. HP uses Hadoop to analyze web user click streams, sessionizing click data and analyzing specific paths users take through the website. Silver Spring Networks uses Hadoop to analyze the constant flow of energy usage data streaming in from smart meters. A leading big box retailer uses Hadoop to analyze customer behavior to guide predictions for product demand. And Ancestry.com uses Hadoop to scan massive sets of genetic data to identify matching patterns. New and never before possible use cases go on and on. So how did we get here? Google is the poster child for the power of the MapReduce paradigm, which underlies Hadoop. Google was the 19th search engine to enter a crowded market. You might recall some of these old search brands, but you might not, because within a few short years, Google emerged and dominated the search market. Google figured out two key technologies to handle the amounts of data they wanted to store and analyze. First, Google developed a distributed storage model called Google File System, or GFS, which became the underlying storage architecture for the massive amounts of data they needed to store. GFS runs on a large array of cheap hardware and is designed to expect and accommodate frequent hardware failures. Google published a paper in 2003 releasing the GFS concept to the public. Then, in 2004, they published another paper on their distributed computing model called MapReduce. MapReduce vastly simplifies distributed programming and leverages the processors that exist on all those servers in the GFS array. The key to these two components is that they are designed to run on low-cost commodity hardware, and that costs scale linearly with capacity. If you need twice the compute power, just add twice the machines. Let's look at the industry trends that made the distributed file system and MapReduce such a revolution. In less than 20 years, the capacity of disks has gone from 2.1 gigabytes to 3,000 gigabytes, an increase of 1,400 times. The cost per gigabyte went from $157 to a nickel, an improvement of over 3,000 times. Meanwhile, disk transfer rate, which is how fast you can get data onto and off of disk, has improved, but only by about 12 times. In terms of how long it takes to read back all data on a disk, the read time has actually been getting longer. So we have an asymmetry in disk technology evolution, which has created a massive capacity for data storage, but a bottleneck in the ability to move data around. Concurrently, traditional storage methods such as relational databases have reached physical limits in terms of handling the data that modern industries need to store and analyze. Big data typically refers to these three aspects: velocity, variety, and volume, any one of which could be a technical challenge. Velocity refers to the rate of data coming in. For example, Twitter recently logged over 400 million tweets in one day. The Large Hadron Collider generates 40 terabytes per second. Traditional approaches can't absorb and organize data at that rate. Variety refers to the kinds of data being stored and analyzed. Structured data in a database is one source for analysis, but today, useful data comes from all over, from web pages, social media feeds, application logs, and in multiple formats like XML, JSON, unstructured text, audio, video, and on and on. It's hard to create a schema if the kinds of analysis you want to do over time will change. And volume refers to the quantity of data, which no one disputes is going up and up. So evolution in disk technology and the inability of traditional approaches to keep up with modern demands are driving new big data solutions. Recall that Google solved these challenges with GFS and MapReduce, enabling them to leapfrog existing technologies and dominate their market. Then they released those two concepts into the public domain. And those are the foundational technologies that form the core of Hadoop, which was adopted as an Apache project in 2006. Hadoop consists of a distributed file system called HDFS and an implementation of the MapReduce framework. This is a good place to chime in how MapR adds to the story. MapR produces a distribution that makes Hadoop enterprise-grade and adds significant enhancements in performance, reliability, and ease of use. For enterprise data needs, MapR eliminates single points of failure, making all components high availability and self-healing with fast recovery time. MapR's enhanced storage layer, the MapR Data Platform, or MDP, maintains compatibility with HDFS, but provides significantly faster and easier access to data. MapR offers enhancements in other areas of Hadoop as well, while always maintaining compatibility with Apache Hadoop. Let's take a conceptual look at what comprises a Hadoop cluster. The cluster is a collection of many commodity Linux servers, each with multiple disks dedicated to the storage pool. The distributed file system makes use of the disks, while the MapReduce algorithm makes use of the processors on each server. The DFS handles data replication, so data stored on any node gets copied multiple times across the cluster. The nodes might be racked in one data center, or they could span multiple data centers for additional data protection. Hadoop clusters scale linearly, so if you need twice the storage, you build out twice the number of nodes. And by doing so, you also make the cluster more robust. Of course, commodity servers will fail at some point. A large cluster could see multiple disks fail every day. Hadoop treats hardware failure as a first-class citizen, fully expecting it to happen and enabling the cluster to heal when it does. The word Hadoop has come to encompass an ecosystem of tools that has grown up to support various aspects of storing, analyzing, and moving data in Hadoop clusters. All of these tools interface in some way with either the distributed storage layer or MapReduce jobs, or both. To mention a few, HBase is a distributed data store that supports large tables. Hive is a data warehouse that supports SQL-like ad hoc querying and data summarization. Pig is a high-level data flow language and execution framework. Uzi is a workflow scheduler system for managing Hadoop jobs. Flume is a service for aggregating large amounts of log data. Scoop is a tool for transferring bulk data between Hadoop and relational databases. And Mahout is a set of scalable machine learning libraries for applications like taking a user's behavior and producing recommendations for items they might like. And there are more ecosystem tools at apache.org. Hadoop ecosystem tools inherit the same qualities of the underlying cluster: fault tolerance, scale-independent programming, and costs that scale linearly as data size grows. Let's talk about MapReduce briefly because it is a paradigm shift in distributed computing, and it is fundamental to the way Hadoop works. Here's a conceptual example of how MapReduce turns distributed computing on its head. In a traditional paradigm, you would store data on a RAID system and then send data to the beefiest multi-core server you can afford, do the computation, and store results back to the RAID. There's a bottleneck on data transfer rate, which is exacerbated as the amount of data grows. Note that if you want better compute performance, it's not a given that you can find a better server, at least not affordably. So there's a bottleneck on compute scalability too. By contrast, in the Hadoop paradigm, we gather data on the cluster and we send compute to where the data is. The MapReduce program is much smaller than the data, and much of the compute is done locally on each machine, eliminating the I/O bottleneck. Then we read the results back from the cluster. If you need more power, costs scale linearly as you add nodes. Furthermore, the MapReduce program doesn't need to change to accommodate new nodes. Let's cover some main points about how MapReduce works. MapReduce is a programming model for distributed computing, and Hadoop gives you the framework. MapReduce splits up the input dataset based on where the data is stored, and as we saw, sends the MapReduce functions to the machines. MapReduce programs execute in 3 stages: a map stage, a shuffle stage, and a reduce stage. Developers just write map and reduce functions. The framework shuffles and sorts the map output so it's formatted correctly to be the input to the reduce stage. MapReduce is a functional model. Given the same input data, map and reduce functions will produce the same output, no matter how many times they're run, no matter where they're run. This simplifies programming for the developer. If a map task dies unexpectedly, the framework can recover by reissuing the task on a different node. In fact, the framework can issue the same task to multiple nodes and take the result from whichever one finishes first. Hadoop takes care of all the details, so developers focus on the data, which is the whole point, not worrying about low-level details like file I/O, networking, process synchronization, or failure recovery. This is a big deal for distributed programming. The end result is a scale-free programming model. MapReduce code written for a megabyte of data can also work on a terabyte and more. Map and reduce functions are low-level constructs, and so most programs will execute in multiple stages of MapReduce. Many of the Hadoop ecosystem tools generate MapReduce code and run jobs automatically to simplify the development process. Here's an example of how one company has gained significant efficiencies in both analysis and storage by adding a Hadoop cluster to their traditional extract, transform, load operations. For their accounting operations, before deploying the Hadoop solution, they would store billing and accounts receivable data into their data warehouse. They would then perform ETL steps on this semi-structured data to produce scrubbed, structured input for their business intelligence tools. MapReduce is a perfect engine for scrubbing large amounts of unstructured data, so they were able to offload their ETL operations to a Hadoop cluster, gaining performance. And because commodity disk space is cheap on a Hadoop cluster, they were able to lower costs by shifting storage for raw, unprocessed data out of a costly data warehouse into Hadoop's distributed storage. The end result was a savings of $39 million in total cost of ownership over 5 years. Here are even more use cases based on Hadoop's Mahout and HBase ecosystem tools. Recommendation mining takes user behaviors, such as what a user clicks on or what they post, and deduces items they might like. This is useful for advertising. Clustering takes a set of documents or items and clusters them into topically related groups. This is great for search applications that need to present items related to search hits. Classification takes a set of pre-categorized documents and applies labels to uncategorized documents. This is useful for pattern detection. For example, given a set of normal transactions, does some new item look like fraud? Massive data stores are increasingly required for many applications to store billions of records of key-value data without a formal structure or schema. These are so-called NoSQL solutions. Here are some closing reflections on Hadoop and processing big data. Hadoop isn't a one-size-fits-all solution for all applications, and it's not just for huge datasets. As always, you have to know your data and processing needs. The MapReduce programming model is deliberately restrictive to make development easier. So for example, it's not well suited for tasks that need to control internode communications and coordination. Hadoop can require programming and is more involved than writing SQL statements. MapReduce is batch-based, which isn't ideal for real-time transaction processing. However, there are exciting industry developments in real-time querying for Hadoop data. Hadoop is more than a replacement for existing types of analysis. We find Hadoop enabling customers to process data in ways they never could before. Although Hadoop and big data are often mentioned in the same breath, many MapR customers are concerned more about the other V's, data variety and velocity. Hadoop is also a good option when your dataset is small now, but you know it could grow by orders of magnitude. To sum things up, the future of Hadoop looks bright. As one indicator of a trend, we searched for job postings including the word Hadoop, and the result is stunning. There has been an exponential rise in companies hiring for Hadoop experience over the past 5 years. From the inception of MapReduce as Google's secret sauce, to the Apache Hadoop project, through a growing ecosystem of tools, to the founding of companies like MapR, which innovate, expand, and add value to the Hadoop community, big data is still at a nascent stage, and we've only seen the tip of the iceberg in terms of how Hadoop can help you leverage the value of your data. MapR looks forward to years to come of innovating with you in solving big data challenges. To learn more, browse to these URLs for video, documentation, and forum discussion on Hadoop and MapR technologies. If you'd like to get started with Hadoop, you can download and install MapR's distribution for Apache Hadoop. A baseline license is free for an unlimited number of nodes and includes all MapR's performance enhancements. MapR also offers options to deploy in the cloud with Amazon's Elastic MapReduce platform or Google's Compute Engine. Visit mapr.com for all the details.